everyone, and welcome to the 50th Porous Media Tea Time Talk. During these challenging times, we have been giving early career researchers working on porous media the chance to present their work to a scientific community around the world. We have been pleased with the engagement from all our viewers over the last 8 months, so please continue to engage with our talks, and if you have any comments, you can type them in the chat and we'll ask them at the end of the speaker's talk. As was mentioned last week, we ourselves in the Porous Media Tea Time Talk crew are a group of growing early career researchers. I am Catherine Spuren from Imperial College London. I am joined today with Maya Rucker from TU Eindhoven, Nara Brandeyo from I've forgotten, sorry, and Arne Massini from Kent University. I will pass over to Maya, who will introduce the first speaker of today's talk.
Thank you, Catherine. Today's first speaker is Arne Jacob. Arne Jacob was employed by the Hydrogeochemistry Group at the University of Mainz, where he is about to finish his PhD in the next months. He worked on different topics regarding the determination of size of REV and invented an MPI parallelized code for an estimation of REV based on fluid flow velocity fields and pore grain distribution patterns. His latest research investigated the effect of nanoporous clays on simulated permeability in CT images. Arne, the floor is yours.
Yeah, thank you and your team for the invitation and the opportunity to share my research with the scientific community. Today I want to talk about our latest research, which investigated the effect of nanoporous clays on calculated permeability of a reservoir rock. It was published in Solid Earth in January and is open access. So if you want to have a closer look at the topic, you'll be able to read the publication there for free.
Arne, can I just interrupt? Your slides aren't showing.
Yes. Oh. Okay.
Oops. Okay. It seems that Arne is having some technical difficulties. He has rejoined.
Okay. Okay, do you see the presentation now?
Perfect. Yes.
Yeah.
It's not in presentation mode. Oh, there we go. Perfect. Great.
Yeah. Okay. It was a joint work of different universities, namely the KIT in Karlsruhe with Sina Hale and Philip Bloom, and the University of Greifswald with Markus Pelz, Georg Rathoff, and Lawrence Waugh. And then us, the Hydrogeochemistry group of the University of Mainz, with Michael Kersten, Frieda Ensmann, and myself. So how was our starting position? We had an outcrop of an upper Rotliegend sandstone from the quarry Schwentisius near the Bebertal village in Germany, with fluvial and aeolian deposition layers, which you can see on the left-hand side. We wanted to determine the exact permeability and the accessibility of calcite, which can be dissolved by experiments. On the right-hand side, you can see our sampling locations where we drilled plug cores with a diameter of 2.5 centimeter in green and mini plugs with a diameter of 3 millimeter. We used the larger plugs for conventional microcomputed tomography and the smaller plugs for synchrotron computed tomography. We conducted the scanning of the mini plugs at the DC facility in Hamburg. During the post-processing, several steps must be taken to obtain a high image quality. This is especially filtering and segmentation. Since there's always noise in the images after reconstruction, one has to filter them by applying image filters, for example, non-local means filters, Gaussian filters, or median filters. The segmentation can be done by using conventional grayscale thresholding, where you just set a threshold in your gray value intensity level of each voxel, which separates the pores from the grains from the calcite, and so on. By doing so, one can determine the porosity and other important parameters like surface area, curvature, pore size distribution, and so on. We did this for each size of the different plugs we had. For the smaller sized plugs, my colleague Markus Pelz from Greifswald conducted FIB-SEM measurements as well to resolve the qualitative and quantitative clay mineral content of the samples. So we conducted permeability measurements by using gas permeation flux experiments to determine the permeability of the plug samples, the larger plug samples. The intrinsic sample permeability was derived from the apparent gas permeability determined for each pressure step using Darcy's law. Since the fitting of the straight line to determine the true permeability values was very accurate, we assumed the experiment to render the permeability very well. We obtained a mean permeability of 2.9 millidarcy for the big plug samples. And in the middle, you can see a rendering of these big plug samples with visualized calcite content in yellow. And the fluid flow velocity fields, which was obtained by applying the Navier-Stokes equations using the highly advanced solvers of geodict. These samples in the middle were scanned by using conventional micro-CT imaging with a resolution of 13 micrometers. The images on the right-hand side have a much better resolution of 1.2 micrometers, while we binned them with a factor of 2 before reconstruction to obtain a better signal-to-noise ratio. When you compare the permeability of the different methods, you can see that they differ a lot. In the larger plug samples, this is induced by the resolution, which is not sufficient for these types of rocks. Saxena wrote a paper about the operating envelope of micro-CT, which I'd like to recommend at this point. Following Saxena's recommendations, the resolution of the synchrotron images would be enough to resolve the pore throats in the smaller plug samples, while the micro-CT measurements with the bad resolutions do not. You can see that the calculated permeability for these big samples are more than 30 times higher than the measured permeability by gas permeation experiments. This resolution effect increases with increasing complexity of the pore throat network. So the upcoming question was, why is the permeability of the samples imaged by a synchrotron still too high compared to the experiments? Well, we did mercury intrusion porosity to determine the pore size distribution in our samples. This method is widely used to determine pore size distribution of a sample from micrometer to nanometer scale. The technique relies on the Washburn equation, where the pore throats are assumed to have a cylindrical shape. But when the pore throat geometry becomes too complex, this might lead to an underestimation of larger pores, while smaller pores are overestimated. At this point, I'd like to recommend the work of Abel, who replaced mercury with Woods metal and showed how large this effect can be. Well, in our case, this meant we only knew that we had a very complex pore structure, and we have a lot of porosity, which we cannot see in the CT images. And what we can see in the plot as well is that many of the pores are still below our resolution, so at 1 micrometer, while we are at 2.4 micrometers in our synchrotron scans. So in order to receive the permeability of the illite meshworks, which are hidden below our resolution, one has to post-process the data which comes out the FIP SEM measurements. Oh, let me switch these slides here. While the segmentation on the original image would be very bad and noisy, one has to follow several steps to obtain a good representation of the true pore structure. First of all, the images should be cropped and aligned, while cropping is necessary since the 2D images of the FIP SEM might contain information from outside of the structure, which you can see around this first image on the left-hand side. And the alignment can be done by using registration modules of geodict or other programs that can do image analysis. The stripes, which are called curtaining effect, can be removed by curtaining effect filters, which enable us to do other filtering as well, like non-local means, for example. As you can see in image C, the image segmentation with gray value intensity thresholding would not work for FIP SEM images. We used the software Elastic, which to segment this by supervised machine learning segmentation. This built-in classification module groups the probability of each pixel to be assigned to a phase according to the different image feature. So if you have a sharp border, that will be taken into account as well as the gray values. Examples of the correct class or phase in our case, provided by the user, builds a decision surface in feature space. Based on these features, a random forest classifier assigns each of the pixels or voxels to a certain phase. This method works for both 2D and 3D. We were able to obtain a very accurate representation of this Illite meshwork using this workflow. Based on this segmentation, we calculated the permeability by applying the Navier-Stokes equation to the Illite meshwork as well as we did it with the synchrotron dataset. So the next issue was, how do we get this permeability information of the clay into our micrometer scale synchrotron data? Well, since we know from backscattered electron microscopy, it was the image I was showing before, that we have a lot of illite hidden in the pore throats, we should be able to model them into our pore throats. By doing so, the modeled clay minerals in each pore throat with a diameter of 2 voxels or less are assumed to contain illites. We did this by using the Euclidean distance maps. But this would have closed larger pore throats with complex topology as well, which is not wanted. So we had to preserve these open pores by a structure element which restores the original shape of the pores. The domains in blue contain the voxel permeability of the illite clays, which were measured by simulating the permeability by applying Navier-Stokes equations. We added this information to all of our samples, which were measured by synchrotron tomography, and calculated the permeability of these samples with Brinkmann domains. On this slide, the workflow is shown for an exemplary sample. We can clearly observe, and we also expected that, the overall velocities of the voxels decrease. You can see on the left-hand side, it is very bluish, which is higher with velocities as on the right side. This was expected since the permeability of the Brinkmann domains slows down the complete fluid flow through the rock. But as you can see, the permeability of the structure with Brinkmann domains fits the permeability range from the experimental measurements, which was 2.9 millidarcy. Nevertheless, one has to be careful when simulations to determine permeability should be applied. In our samples, few samples showed a very bad distribution of the flow path. You can see that on the left-hand side, that the structure's largest flow paths are more or less evenly distributed, while on the right side, the flow is controlled by only 3 or 5 pore throats. This occurs when structures are cemented by calcite or other pore cements, or the resolution is just too low to resolve the pore throats. The results would be an inaccurate permeability calculation of that sample. In the most common case, the permeability would be calculated too low. We did not include these samples with a bad flow impingement into our calculations in order to preserve accurate results. So this is the main figure from our last publication, while you can see on the left side that the range of values for the gas permeator test experiments is around 1 to 5 millidarcies. And in the middle, there are the simulated permeabilities based on the original CT images of the samples. On the right side, you can see how the range of values would change when we model Brinkmann domains, which contain the permeability information of the illite meshworks into our samples. The black lines show the mean values and the red lines the median values. This figure illustrates how inaccurate the calculations would be without including the clay permeability of the illites into the scans. When we simulate the permeability only on the original images, sorry, that was my fault. We would be 100%, we would be 800% above the permeability which was determined by gas permeation flux experiments. When we include the information we have from FIB-SEM imaging, we are very close to the true permeability values, which are coming from experimental measurements. So around 1 to 5 millidarcies. Yes, with this, I want to close my talk, and I want to thank you for your attention.
Yes, thank you, Arne, for this very nice presentation. To our audience, if you have any questions, please type them in the comment section, and I will read them to Arne for you, and so you can answer the questions. And while we wait for people to write their questions, I have a couple of questions. First of all, So you calculate the permeability on your FIPSEM volume,
Mm-hmm.
which is, of course, a rather has a limited field of view.
Yes.
Especially the thickness is rather thin. So I was wondering, how sensitive is your model to any changes in permeability, input permeability from the FIPSEM?
Well, it depends more on the distribution of the Brinkmann domains than on the absolute permeability values. I checked it for a plus minus a factor of 10 with the Brinkmann domains, and it did not change much in the permeability after the modeling. But we assumed the mean permeability calculated in all directions of the FIP-SEM data. So we calculated that in X direction, Y direction, and Z direction, and mean these permeabilities, and took this value to put it into our model. Okay. So my colleague Markus Pels works on another paper, which includes other clay mineral topologies as well. And then we might be able to get even nearer to that absolute permeability value we have from experimental measurements.
Okay, thank you. And so far, we have not received any other questions. So then I have another question. So you also investigated the REV and the effect on the REV sizes.
Yes.
Can you maybe tell a little bit about how big the REV, have you investigated the REV for these samples as well? Like how big your volume of your micro-CT volume needs to be to include all the heterogeneities related to this heterogeneous illite distribution?
Well, we use a different approach than this growing sphere approach. I wrote an algorithm and a code which determines variances based on the voxel velocities taken from the Navier-Stokes equations. And what I can say is that in our model, this would be in REV range for these microplugs, which have a diameter of 3 millimeters. It does not only grow a volume from the middle or from the center of the sample, but it always includes every voxel in the sample. So what we would have is a good representation of the variance of all voxels along one of the main directions you calculate the variance in.
Okay, thank you very much. Then if there's no further questions, I think we can move on to the...
I actually have one more question.
Sorry.
Yes.
And the last image which you showed on slide 10,
this one?
the error bar, yes, the error bar, is it based on the different samples, or did you also do some, is it also including the sensitivity to your selected domains? So is it just different samples which is in the error bar, or did you also manipulate some of the...
Yes, it's just the different samples.
Okay.
And what you can see is that the range of values is far too high in the middle. You can see that the values are between like 7 millidarcies and 50 millidarcies.
And have you also compared the value, the error here to the sensitivity of your input parameters?
We do this in the next publication, which is hopefully going out in the next month. But we're still on it. So you can expect that it will come.
Can you tell us already what parameters you checked? So what did you evaluate? So is it just the image processing? What kind of comparisons did you do?
So what we already know is that the image processing is very important because even minor changes in the pore throat distribution might have a large impact on the permeability of samples. Yes. We assumed after Saxena that our scans were very good. Yeah, we had a good resolution, and that we were able to resolve the pore throats very good. So as soon as there are no better synchrotron measurements below 1 micrometer, I'm not sure how we should resolve this. Yeah.
Okay, thank you. Looking forward to the paper.
Okay. Then maybe we can move on to our second speaker. So our second speaker of today will be Ray Payton. And he's a third-year PhD student at Royal Holloway University of London in Earth Sciences, in the Earth Sciences department, and he's doing his PhD together with the British Geological Survey and Oracle. He completed the undergraduate degree at Royal Holloway in environmental geology in 2018 and moved on to work on his PhD project there as well. He is interested in microstructural properties of rocks and how they influence the fluid flow, with a particular focus on geological carbon storage. Today he will present a presentation titled Pore Scale Assessment of Subsurface Carbon Storage Potential Implications for the UK Geoenergy Observatories project. With that, I would like to welcome Ray Payton, and yeah, the floor is yours.
Cool. Thank you very much, Arne. Yes, thank you very much for the introduction. So, like we said, I'm going to talk a little bit about the UK Geoenergy Observatories project and how the work that I've been doing feeds into that and how it relates to carbon capture and storage. So a little overview for the beginning, if there's anybody who isn't sort of too familiar with CCS. So ultimately, what we're doing is injecting carbon dioxide into the subsurface, into some sort of porous reservoir for long-term storage. There are a number of different processes which happen in order to store the carbon. I won't get into too much detail with those today, but ultimately the things which govern these processes are the porosity, permeability, and a few other features as well. But ultimately, porosity and permeability are the key features which we're looking to try and characterize from a given reservoir to determine whether it could be suitable for carbon storage or not. The fluid has to move throughout the porous medium. So the porosity is telling us how much space there is to be able to do this. And of course, the permeability is effectively how easy it is for the fluid to move throughout the reservoir and make the best use of the space. So I also use some of the techniques which you were just hearing about. Predominantly, I'm using micro-CT. So obviously this is where we see X-ray attenuation displayed in grayscale, where here we can see some, the paler features are the grains and the darker areas are the pore space. And ultimately segmentation of these phases allows us to make measurements related to the solid material and the void space fraction. So the sorts of images that we're getting from this give a voxel resolution of between 1 and 5 microns, depending on what the sample is. And typically there are about 1,000 slices in a given sample in order to reconstruct a 3D volume. So these are a couple of examples here. This is a really nice porous sandstone, and this one is a really horrible cemented sandstone with very, very, very limited porosity in it, which I'll show you a bit more about. So these are the study sites which I've been working on. These first two over here in Glasgow and in Sellafield are directly related to the UK Geoenergy Observatories project, which has been run by the British Geological Survey. The first site is up in Glasgow, which is where this material is from the Scottish Middle Coal Measures Formation. And the idea of the UK GEOS is to develop subsurface laboratories in order to experiment with different low carbon technologies. So I've been able to obtain some material to perform some preliminary analyses on. And then there's also going to be a second site in Cheshire, which is currently under construction. So what we did is we decided to choose some samples from a little further north in Sellafield in Cumbria, because the Wormslow Sandstone Formation is a lateral equivalent of the geology which we expect to be drilled in Cheshire. So we're able to perform a preliminary analysis. I've also obtained some samples from the Porcupine Basin off the coast of Ireland. This area has been explored for hydrocarbons. So we thought it would be interesting if we could perform some analyses here as well to see whether this is something else which could provide some possibilities for CCS in and around the UK and Ireland. So the first sort of measurements which we can make are total and connected porosity. So here's a 2D slice. All of the darker phase, which is the pore space, has been segmented here using a mixture of automated and manual thresholding algorithms. So the total volume fraction here we can see is the total porosity in these yellow bars. All of these samples with lots of porosity are from the Sellafield site. So we can see there's lots of porosity present. However, in that cemented sample from Glasgow, very, very limited porosity. We can also then run through the full 3D image stack, an algorithm which will determine how much connected pore space there is. And we can see that the connected pore space here in blue is very similar to the total porosity in the case of the Sellafield samples. And this is really interesting, and I'll show you why that is in the coming slides. However, because there was no connected porosity at all in the Glasgow samples, we can determine straight away that this isn't really a suitable site for looking at carbon storage as a type of low carbon technology for this particular observatory. These are the porosity results from the Porcupine Basin. There's a bit more variety which we were able to pick up. We can see there's a bit more of a discrepancy between the connected and total porosities as well, which is something which is really interesting. Our results are around sort of the 10% porosity mark, which is a really crucial value, and you'll understand why this is as I get into the next few plots. So what we can do is we're plotting the total porosity against the connected porosity here. The blue points are from the Sellafield samples. The green points are obviously from the Glasgow samples, which we decided on aren't particularly interesting. However, we've also got some supplementary data points from another member of the research group at Royal Holloway. Now, what we see is this one tool is increasing, connected porosity is increasing too, in the same sort of order. However, around the 10% porosity mark and below, we see this sort of deviation from this trend line. And this is interesting. We can see this more clearly when we plot the ratio on the y-axis of connected and total porosity, that this sort of drop-off point is far clearer. Now, what this actually is the percolation threshold, or some people call it the connectivity cutoff. And what this is at 10% porosity, anything above this, we can show that there is almost full connectivity. However, once we hit 10%, the connectivity decreases significantly, and we end up with a situation where we have partial connectivity, and then below that, no connectivity. So this 10% value is super crucial, because if we can analyze rocks and say, okay, there's 10% total porosity, and we decide that that is our percolation threshold, then anything above that should be able to provide a good level of connectivity, which is a desirable characteristic of a potential storage reservoir. We've been able to look at this in a little more detail by plotting the results from the Porcupine Basin. And what we're able to see is, because, as I was mentioning earlier, the majority of the data points were around that 10% mark, we were hoping it was going to be able to better define that, that percolation threshold. So we can see that there's a good agreement up here following the one-to-one line, but down here there's a bit more deviation, and these data points a little bit further up, maybe around the 13–14% mark. So we're hoping with time, as I can analyze more samples, we'll be able to better constrain where this percolation threshold is, as it's such an important value to characterize reservoirs with. So we're also able to make permeability measurements as well. We run single-phase Stokes flow through the pore network, and we can see here that with the Sellafield results, because they're up on this end, we get this trend, this nice sort of trend here that you can see while using the data from the literature. But as we hit that 10% mark again, the literature data starts to show a kink and starts on a different trajectory. So we're hoping that once I've managed to complete the permeability simulations, we'll get more data points around here and sort of see where that kink starts to form in our data, and again, better constrain that permeability, that percolation threshold. So we're also able to describe a few other things in a more qualitative sense to then derive some more quantitative results. So from these image stacks, we're able to extract the total porosity, which you can see in blue. And then in red, you can see just about up here, these tiny little speckles are the disconnected porosity. Now, in this case, we can see that the majority of the disconnected porosity is actually intragranular. So where these voids are left where the grains are, which have been segmented out, this is where the majority of the disconnected porosity is forming. However, in this sample, we can see that there is much more, a greater proportion of disconnected porosity, but it's not really taking on that same form. It appears to be more intergranular. So this is an interesting observation to make. So we can then build a pore network model, which I'm sure many of you are familiar with balls and sticks representing pores and throats. And we can then make measurements from there to further characterize the pore structure. So if we have a look at these plots on the left-hand side to begin with, at the top here, what we've got is pores down the left-hand side and throats down the right-hand side. And the top two are for total porosity and the bottom for connected porosity. So what we're seeing is that in the total porosity, there's this large portion of very small pores, which can be explained by those intragranular pores that I just showed you, because these aren't contributing to connectivity at all. Down here, where we look at the connected case, all of these smaller pores are lost. So it really is the larger pores which are contributing to the connectivity. In some cases, you may find that the smaller pores are crucial to connect the larger pores together. But this doesn't appear to be the case in what we found here. It's the same case for the throats as well. We can see that these smaller throats are lost when we look at the connected case. So again, the larger pores and larger throats are really crucial to the connectivity here. Over on this side, we measure a few different characteristics such as pore radius, throat length, and coordination number. And the hollow circles are for the connected porosity, and the filled sample circles are for the total porosity. Now we have a discrimination between the two here because of those many small pores which are incorporated into the total porosity, but the hollow circles aren't showing that, because as we see over here, that the small pores and throats aren't contributing. So as expected, the porosity is increasing as the pore radius and throat radius and coordination number are increasing as well. So we've been able to provide a good detailed characterization of these samples. So ultimately what this means for linking to CCS is that we've been able to isolate the percolation threshold and constrain it reasonably well, which we're hoping to do further in future. We can show that the Wilmslow sandstone formation in Sellafield warrants further investigation relating to carbon capture and storage. And this shows promise for the Cheshire UKGeos site. The Glasgow sample area has no real merit for investigation for CCS, but other investigations are ongoing for other low carbon technologies in that area. And the Porcupine Basin is sort of on that cusp, as we found that most of the measurements are in the 10% zone. So it will be interesting once we're able to complete the permeability simulations to obtain those results and see what that can tell us. So thank you very much for listening.
Thank you very much for the nice presentation. Yeah, the presentation is now, of course, open for questions. You can ask questions by typing them into the chat in the YouTube channel, and we will read them out and ask them to the speaker. I don't see any questions yet, but I have a few, so I will just start. My first question is the same as to Arne before. How did you address image processing artifacts? So did you look into the sensitivity of your results to image processing?
Yeah, so as we know with any image processing, it's a big challenge to try and reliably take out your pore space in this case. So we did a bit of experimentation with the automatic and manual segmentation methods. We found that in terms of filtering and the pre-processing, that was we determined that we got the best result that we could out of it in terms of using things like non-local means filters and sort of improving edge sharpness. So we determined that that was the best case, and we figured that that was safe to then move on with. We decided to present results using an automatic OTSU algorithm, sort of guiding it based on when there was a tight discrimination by what we could discern by eye was definitely not the pore structure, used in combination with some optical microscopy. We were able to feed it an upper and lower value so that we could get an automated segmentation through the middle. But in some cases in the Glasgow samples, that was really difficult to try and perform that measurement. So we actually had to implement some manual thresholding using a histogram for that. So it was tricky, and ultimately we tried to make it as automated as possible to remove the user input bias. But that's why the error bars on the plots for porosity are shown with the results given for automatic algorithms, and then the error bars are for what's shown plus minus with the manual interpretation. So there was definitely a bit of wiggle room, but we're confident in the automatic segmentation.
Yeah, it was, of course, you showed that the disconnected pores were in particularly small, right? So you would expect to have a larger error in this part. Oh, you don't. Yeah.
It's something which obviously we tried to make sure that those pores that were picked up weren't due to any noise in the images, but after all of the filtering, they were still present and quite clear once you sort of zoomed right in. So we did believe that was part of it, but obviously with features that are that small, when your resolution isn't necessarily great enough to fully resolve them, yes, I would say that there was probably a little more room for maneuver in there, but ultimately the overall result I think is still pretty representative.
Thanks. There are some questions now in the YouTube channel. One is by Mohammad Noura. I have a question about scale awareness. How can post-scale observation be translated to Darcy continuum scale reliably when it comes to fluid flow or reactive transport during surface CO2 storage, subsurface, I guess?
Yeah, this is always a really difficult and challenging thing to address. Everybody that works at the pore scale, ultimately everybody always wants to be able to upscale. It's not something that I've been focusing on trying to do in my own work. I've just been focusing on microscale characterization and trying to make those sort of pull out those key measurements as I was talking about earlier. But there are methods out there in order to try and generate sort of things like numerical models using a combination of microscale and Darcy scale, and then deriving sort of a unified at the pore scale, but also be aware that we need to make sure that there is a way when you try and have that application to use that information reliably for the larger scale. There's no point performing measurements and simulations at the large scale without considering what's going on at these very small scales, because this is what's the fundamental and underlying processes that are going on. So it is a big challenge, but not something that I have too much experience in, and something that I'm not doing too much on with my project.
Thank you. There's one more. Two more questions. The next one is, you propose that 10% porosity can be considered as a universal percolation threshold. What are your thoughts for the influence of age and type of rock on this percolation threshold value?
Yeah, that's a really interesting point. So yeah, so 10% is what I've found throughout the samples which I've analysed, and everything that I've worked on has been sandstones. So I know that, for example, in carbonates, this value varies a little bit. I'm not entirely sure, but I know it's not exactly the same. And also, if you look into things like vesicular basalts as well, I remember seeing a paper which had shown they had a percolation threshold around the 25% porosity mark. So it's definitely not a completely universal value, but for the samples which I've looked at, that does seem to be the case. Hopefully with more samples to be analysed in the future that are in the pipeline, like I say, we'll be able to better constrain this. In terms of age, so I guess, what I just said kind of covers type of rock, but in terms of age, that's all going to depend on ultimately, if you have things like compaction and deformation, then that's going to alter your porosity and your connected porosity as well. So we would have to explicitly choose samples to study that have undergone such processes to better define this for that case. But in terms of what I've been looking at, 10% seems to be a good indicative value for these particular samples.
Thank you. So the question was asked by Hector Moreno. Thanks for posting. And the last question in the chat is by Sharon Ellman. Great talk, thanks. Is the percolation threshold expected to be the same in other types of rocks? What kind of parameters do you think control percolation threshold?
Again, good question. So yeah, I guess I just already touched on whether it be the same in other types of rocks. So no, that's not necessarily the case from what I've seen, but not measurements that I've made myself. In terms of other parameters that control the percolation threshold, I guess we were talking about the size of the pores and the connectivity. It all kind of comes down to that, really. If you have lots of small pores which aren't connected, then that's going to have an impact on where that percolation threshold is. Because those measurements from the Porcupine Basin show total porosities of more around the 10% mark, I'm hoping that because there was that little bit of deviation where they were showing that maybe it could be closer to 13–14% in that particular case, I want to sort of dig down into that and see why they're showing that skew. It could be because there is that greater difference between the total and connected porosity, and then I want to know what's controlling that. What is the reason for that? So there's still plenty more work to be done on those particular samples to try and better constrain what the parameters are which are controlling the percolation threshold, as you say.
Thanks. We have one more question from the background. Naga, I'm not sure. Do you want to come to the front and ask yourself, or shall I ask for you? Okay, well, I will just go ahead. In slide 11, is the frequency of number? I mean, was it calculated based on the total number of roads or pores?
Yeah, so this frequency here is the total number of throats and pores, but it's normalized, and we've got the log down here, so that's why it's not up in the thousands and tens of thousands. If that's what you were questioning.
Okay, so it seems like this question was answered. I have only one more question for the disconnected pores. Is it possible that these are still connected through micropores which you cannot see? And in this context, have you considered looking into some analysis like Arne proposed before to address?
Yeah, this is really important to consider. Yeah, it's important to say that everything that I've presented is based on macro porosity. Because of the resolution of the images, we wanted to make sure that we were fully characterizing the samples, and microporosity is always a big part of that, because obviously, as we've seen, microporosity can control the overall porosity quite significantly. So we did some optical microscopy to have a look at some of the questionable areas which showed up in the grayscale images from the CT to try and see what was going on there. And we were unable to see anything like extra sort of mineralization, sorts of clays and that sort of stuff that didn't appear to be present. It would be nice to carry out some higher resolution imaging if that's something which becomes available for me to do, and then be able to try and factor that in if there is any microporosity present. There are plans potentially to be able to do some FibSem to look into that. But yeah, currently everything that I've shown is based on the assumption that this is the macro porosity. But of course, the micro porosity is something that's incredibly important, particularly in those Glasgow samples, which are so heavily cemented. If there were a lot of micro porosity present there, then that could be a real game changer for what the overall porosity is. So yeah, so currently, based on macro porosity, this is what we see, but it would be really nice to consider the micro porosity too.
Thank you very much. And with this, I think we are closing the session for today. We thank our two great speakers for the talks, and the audience, of course, for posting questions and listening. Thank you very much. Our next talk yeah, our next Porous Media Tea Time talks are 23rd March this year at 3 p.m. CET. We will hear Oliver Paulin from Oxford University and Tiago Quinolato from the Institution Federal University of Juiz de Fora. We are looking forward to see you again next week, and would like to thank, in the name of all our colleagues supporting the Porous Media Tea Time talks. Thank you, and see you again next week, 2 weeks.